Okay, so folks who are remote, I hope you can hear me. The important announcement is that whatever you type on the chat can be seen by everybody. So in case you want to write something just to me, I would suggest writing it in email. I'll address it after the class. Okay. Otherwise, you can use the chat. Ideally, I would suggest you guys, use a mic to, say something. Okay. With that. Okay, let's get started. So we are in week 3, and assignment one has been there since the beginning, but it's due soon. Yeah, it's due next week, I guess, next in 6 days. So we'll briefly discuss some of the hurdles that some of you are facing. Since some of you brought to me, I assume many of you are facing this hurdle. And it's a good point. I'm going to spend a couple of minutes on discussing something about assignment 1. So we are here. So it's the 3rd lecture. It's going to be, I think, the very interesting lecture because we're really going to finish up convolutional neural networks. So although last time we were towards the end and we kind of didn't get a good sense of what a con layer is, we're going to discuss that. And so by this lecture, you should be decently confident to tackle assignment 2, which is actually a big part of that is related to CNNs that we'll talk today. And in particular, there'll be need for GPUs. And that's why I'm suggesting with assignment 1, even though there's no need for a GPU as such, to get used to, let's say, Google Colab, or if you have your own GPU enabled machine like your laptop, then try to get used to like GPU. Now, the question is like, what is meant by getting used to a GPU? It's basically, in the second assignment, you'll be using PyTorch, and then we saw a quick demo of PyTorch, I think, in the last lecture. Right, with the regression example. So PyTorch is very similar to NumPy. So NumPy, I guess, linear algebra is assumed as a prereq. So you should be comfortable with matrices. Tensors we'll talk about again today when we talk about depth and so on. So you are getting slowly acquainted with things which were not standard before, right? So before you're basically working with tables and matrices and so on at most. Now you're going to talk about tensors, and PyTorch tensors can live in the regular memory, which is the RAM, or in the GPU memory. Okay. So when I say make use of the GPU, I just mean if you have an image, if you read the image, let's say, with imread or one of these auxiliary functions, after that, if you want to put it in a GPU memory, so that if you put the red image, let's say a tensor or basically a data object, you can put it in the GPU memory. You can put your model also neural network model, let's say P-power neural network or something like that. You can also put it in the GPU memory, and then you do backprop. Okay, that's going to be efficient than doing the same thing on CPU. So if you don't have a GPU, for example, in a laptop, and you're using, let's say, Anaconda Python, and if you install PyTorch, for example, or TensorFlow, they're going to be CPU versions. Hopefully, you can check the version. You can look at the package name. It will say _CPU, for example. So those ones can also do backprop, using the regular RAM and using the CPU, strengths, but they're going to be relatively slow. Okay, so that's the whole point of deep learning, needing these computational resources. Okay. So anyway, so all that is kind of going to become very critical for assignment 2. Assignment 1, you can try out, sending things to GPU or CPU. For example, in PyTorch, there's a very simple way, you can do toDevice, and device is just a string where you can say, hey, use the CPU or GPU and so on. Okay. Like, if you have a variable like tensor, some variable .to TO, and then put a bracket, then you actually send it to one side or the other. Okay. So these are things that you will slowly learn. In assignment 1, I know we have to use Keras and TensorFlow, which kind of makes things super easy. But by assignment 2, you want to kind of ramp up, to using something more, get used to PyTorch way of doing things. Okay. Anyway, that's like, I know it's a few weeks away, but I wanted to quickly mention that what we're going to cover today, and we're going to kind of stop. We're going to switch topics next time. Next time it's going to be about NLP. Okay, but whatever we cover today is relevant for the submission, which is due in about a month, less than a month. Okay, so just so that you can pay attention, or at least you have enough bandwidth to kind of get started if you want. Okay. So As I said, we were here in lecture 2, and I'm going to mention the lecture goals in a second. We briefly started CNNs, and I was talking about rearranging neurons and at least making it into a 2D thing, layer view. But from 2D view to how to think of depth and neurons, that we're going to continue on that. And we'll also mention what is pooling. So that pretty much captures the essential building blocks, a layered wise building block of neural networks. So think of neural networks as basically consisting of Lego blocks. These are not Lego blocks, but layers, and you kind of chain them together. Okay. So today's objective is really, when I say jump starting CNNs, it's mostly about using pre-trained CNNs, which is that somebody else has already trained, did the backpropagation like 1,000 times, 1,000,000 times already on some data set. And then you use the pre-trained thing to further train. Okay. And that's the core idea in what is called transfer learning. And so we'll that's the core idea for today. Okay. So that's the agenda for today. The remaining things are, I'll discuss them when we get there. They're more about a dropout as a regularization or something related to weight initialization. I think we talked about briefly when we did review that the starting point matters. The moment you have a loss function, which is not, like a simple parabola or a ball type of a thing. So those are some practical considerations. We'll look at that. Okay. So that's the agenda. I don't know if, yeah, we have the goals. So we'll continue with where we left off last time. So these 2 points. So by end of today's lecture, and please, ask questions or add comments. Okay, it doesn't have to be questions. You can also add comments if you know something from outside and you read something elsewhere. We're gonna try to finish up this construction of a con layer and understand how it works. It's actually not complicated. So just like in a linear layer, it was just a matrix vector multiplication. Con layer essentially also does the same at the end of the day, a matrix vector multiplication if you vectorize things. But we'll look at the end of the day, from the computer's perspective, it's just going to be matrix vector multiplications going on. But from our interpretation view, we will interpret why a con layer is slightly different in terms of it exploits some properties. Like local connectivity and scale, spatial invariance and parameter sharing and so on. We'll look at those properties that come because we think in terms of filters and so on, and we'll get to that today. Okay. And then pooling is a pretty straightforward idea. We'll talk about pooling. Pooling is just trying to, if you have 10 numbers, instead of 10 numbers, I want to only keep 5 numbers. You take average of, let's say, 2 of them, every pair them up and take an average, things like that. But that's what pooling is. So we look at pooling, and there are 4 more goals, which is as I said, the content of today's lecture, which is most important thing is how to transfer parameters, how to transfer or use the knowledge or use whatever is learned. So whatever is learned is captured in the weights of the network, right? Weights are just the parameters of the network. How do you reuse them for new tasks? And there's no magic, happening here. You might as well just reuse the pre-trained model or slightly change its weight so that it's adapted to your situation. Okay, so your particular esoteric data set may be internal to your company, whereas the model you're getting is from, let's say, an open sourced model by some other research lab or something like that. Okay. But we'll start with a more basic aspect, which is when we talk about CNNs or even feed-forward neural networks, once you've trained them, how do you understand that they're actually picking up the right signals? Okay, and there are some few ways that will be useful. For example, even in your project, okay, to kind of do it as a to get a sense that did the network actually learn something? Okay, and it will make sense for CNNs, and we'll see that. That's the second objective. There are a few more empirical ideas that have come out to kind of further strengthen the way these things are trained. Okay, these are very fragile, crazy functions. Okay, you have, the most complex functions you might have seen in, let's say, 572 or 575 would have been random forest. Okay, random forest, if you really think in terms of functions, there's like a decision tree. Like if you really write it on a function, it looks very messy. Okay, but here you will here also you'll see, our neural networks, right? The reason why there's a deep is that once you think of these Lego blocks, if you put 100 Lego blocks one after the other, then it becomes, that becomes a deep network structure. It becomes super hard to train them. Okay, and that was something that it's still super hard if you start from scratch and just define the network like that and try to train it. People have figured out some ideas. Like here, I've written a couple, but we'll see a few more. Okay, weight initialization is one. dropout idea is one, batch normalization is one. So these are just empirical ideas that people have figured out how to be able to train such deep networks. Okay, anything beyond, let's say, 2 layers, 3 layers, how do you deal with it? 2 or 3 layers is still okay. I mean, you'll be able to successfully train, especially if you want to do it in your projects. But the moment you have 20 layers or 1,000 layers, it's going to be hard. Some people have tried it and figured it out. And so some engineering ideas are here. And another idea which is not related to, specific to images, but can also probably use for slightly other data sets, is the idea of data augmentation. So images have this certain property, right? So spatial invariance. If you're detecting an object, whether the object is in the top right corner or in the center, it doesn't matter. It's still the same object. So you can, given an original input image, you can kind of shift the image or crop it randomly and still expect that the original object that you're trying to, let's say, classify is still there in the image. And so that's the idea. That's the idea in data augmentation. So these are there seem to be a lot of connected topics, but they're all under the idea of enhancing, the vanilla CNN architecture that we'll try to finish today. Once we look at the architecture, the forward pass, then we look at these specific empirical ideas. Okay. So any questions of where we're going? Today will be kind of pretty much about vision, vision as in like images. We'll not, of course, not talk about video, how to classify videos and stuff. But CNN is the most, I guess, basic architecture in this domain. So it's good to understand it ins and out of this thing. Okay. There are no questions. Let me get in the topic, but before that, let me briefly comment about the assignments. So first of all, assignment 1, how many of you have not started it? Because there's only 1 week left. Nothing to be embarrassed about. I'm sure people have other courses and other obligations, so do get started. If you have not started, ideally you should take about 2 weeks to kind of finish this as a group. Okay. If you want more challenge, you should do it individually. It's not, the sky is the limit for you. If you really want to be a deep learning expert, whether as a business analyst, a manager, or even a data scientist, this is a good time to experiment, okay, and fail. And it's not even like, for example, if you're using Google Colab, it's not your own machine. You're not going to crash it, okay? So you make use of the resources and get started. So I think the challenging part will be not number 2. Number 2 is actually just demonstrated in the class. I just did a regression example with PyTorch, but you don't have to use PyTorch. You can just do gradient descent here. Number 3 should be just Python basics, how to define anything, a function, basically. So number 4 and number 5 are, I guess, the more challenging parts. So I think yeah. So number 4 is already, I guess, already given in your example code. So examples, feed-forward networks. If you look at feed-forward, feed-forward network, and then you look at a linear classifier example, that exactly is your multi-class logistic regression. I think the rest of the work is mostly trying to, that script was not even doing anything, right? It was just saying test data is the same as training data and so on. But if you want to do, if you want to robustify it, you need to actually create data, split it into training and validation, and do it properly. Okay, so that's what this is about. And then trying out, hey, what is the number of neurons? Number of hidden neurons is like 10 instead of 100, which is, I guess, in that script. Or if it is 1,000, then what happens? It's good to understand and get some intuition. Okay, and this is it may seem like it's unclear. Like, it's not going to be a landslide change in the performance if you go from, let's say, 100 neurons to 200 neurons. There's going to be probably a slight change, and the data set is, by the way, very easy here. If you want, you can change the data set if you want to try out things. Okay. The challenging one is number 5, and this is where understanding that script becomes important. So for number 4, understanding linear classifier, let's say, start with linear classifier, because the feed-forward network is almost the same, except it has 2 additional, it has 1 hidden layer, right? 1 hidden layer or 2-layer neural network, whereas the linear model is just 1 layer neural network. It's a degenerate or the base case. The challenging part for both of these scripts is to understand what's going on in this for loop. Okay, and in this for loop, I really suggest breaking it into parts. Okay, first part is just understanding the forward pass, which is just getting up to this loss. Okay, given any set of parameters, W1, B1, W2, B2, or WB, W2, B2 in this notation, why does this way of forward pass and getting to loss make sense? Okay, there is already some vectorization going on. For example, here, I hope people can understand, what is this? Okay, these probes and scores, they're all NumPy arrays, or NumPy arrays here. So indexing NumPy n-dimensional arrays is important, and that's what's going on here, for example. So understand the forward pass really well. Okay, and then the second part, here it seems quite long, is to get the gradient of the loss with respect to the parameters. The 4 parameters, WB, W2, B2, and at the end of the day, these 4 variables here are supposed to get the gradient of the loss, one number, like one scalar value, right? Loss is like 10 units or something. That with respect to your parameters, right? So that's what is being evaluated from this point onwards, from here to here. It's not complicated. Okay, if in the class we did in the class as well as in assignment 1, we have at least some more exercising into how to get gradients of complex gradients of functions, right? Gradient of f with respect to a, b, c, d, e, for example, you can break it down into parts and use chain rule, right? So you can also use chain rule here. Okay, and for example, you can contrast this script with the linear classifier example to get a sense of, because of this one additional layer, what additional computation is going on. Okay, so in fact, you will see that up to this point, the code will look similar. Okay, and then from W2, there's also W in front, so there's one more local gradient to be computed and multiplied together. Okay, so I strongly suggest understanding this code step by step. It's a nice exercise in understanding linear algebra, NumPy, backdrop, and I guess those 3. So, and then the last part is exactly your simple gradient descent. Okay, so W is old W minus step size times gradient of loss with respect to W. So if you really wrap around this script, then it'll be a little bit more easier into what's going on behind the scenes. Otherwise, everything will look like an API, a high-level function call like solve my problem. That's not enough, right? You need to know beyond calling like a very high-level function. So okay, so I guess those are my quick comments on assignment 1. Does anybody have any immediate question right at the moment? You can always ask. Yeah.
So for the last one, right, the feed-forward networks, do we
yes.
have to make it from scratch, or can we just use TF and Keras directly?
No, I would suggest use the script. Okay, the script is almost the same as that, right? Except for
it does the same thing, but just like 2 lines.
Except for no, it's not exactly probably 2 lines, because you want to change the function, right? The nonlinearity. So it's not going to be just a change of 2 lines. Okay, it's going to influence something here. Okay, so the backpropagated gradients, like here, for example, because of ReLU, something like this is happening. Because of that leaky ReLU, or whatever that definition is there, something slightly different is going to happen. Okay.
So when you say build using Keras and TensorFlow,
that is also part of the assignment. Yeah.
We need to build it using Keras and TensorFlow, and we need to write the code.
Oh yeah. Okay. Sorry, I didn't check this. This is the Keras part, right? So why did you even ask this question? Sorry.
Do we need to do both or just one? Because what you explained is the scratch part.
Okay. Yeah.
The previous question is a linear classifier, right? It's not a FFN.
No, it is, right? It's a 2-layer. This is a linear classifier, right? Yeah. Okay, so I guess I probably simplified this. Let me just check correctly again. Yeah, this is fine. Consider 2 models, and then build your classifiers using Keras and TensorFlow. Okay.
So what I have done is I've built both those models using Keras and TensorFlow.
Okay, that's good.
I've just changed the activation to the KRU.
Yes. Yeah. So that would make it super easy. Okay. Yeah, this is optional. Okay. So if you can solve this problem as it's stated here, which is exactly use Keras and TensorFlow. We'll not be using TensorFlow much for the rest of the assignment 2, 3, and 4. We have to stick to something, right? One of the packages is good enough, so we'll stick with PyTorch. But yeah, getting to know a little bit about TensorFlow and the basics of setting up a Keras model, which is a nice, simple, straightforward way to do set up a neural network. That's what you will learn here. If you want more challenging, if you want it more challenging, you can use the feedforward network code and then change the change the nonlinearity. Yeah, it's a good question. I thought it had that part. Maybe I deleted it. Yes. Yeah. Okay. I guess that clarifies things. Then I guess the assignment should not take much time. Yeah. Any other question? Okay, that's a good point. Thanks. Okay, I'll close this assignment and we don't need this for now. Okay, I think we can get to, maybe we'll look at codes. The code is going to be useful for your assignment too, but I think we are jumping too much ahead. Let's actually look at CNN, the intuition and the basics first. And if you have time towards the end of the class, we'll look at the script. Okay, and the script involves PyTorch, which is what I tried to introduce last time. Okay, that was a tangent towards assignment. Let's come back to our slide deck. I hope everything is shared here, right? Oh, what happened to? Oh, it is shared. Okay. Yeah. So I'm just getting, I'm going to quickly recap where we were. So feedforward neural networks, as I said, a illustrative way to look at it is in terms of layers. Think of input layers and degenerate layer. Input layer just means the input numbers ready to be pushed forward into the network. Network is just a function. It's just we are just using the names, interchangeably. So each layer, which is not either the input or the output, is basically a hidden layer. Hidden, again, just to say that it's not exposed to either the inputs or you're not taking those outputs by yourself. So outputs for some other purpose. So this is a layered view. Okay, so it resembles almost close to a computational graph. It's not exactly computational graph because we need to say what's going on in each node. But we did mention that last time. In each node, basically, there's weights associated with it. There's an inner product going on, and there's a nonlinearity being applied. That's all. So if you had more layers, you just think of further connections down, further connections to the left, to the right of it, and eventually there will be an output. Okay, output layer. And the output layer is basically those cores. Okay. Yeah, basically those cores, and then you do a softmax to get probabilities, and then or quantities between 0 and 1, and then you pick the log loss appropriately. Okay, the softmax loss if it's a classification problem. So that is good. So what we're going to now change is the input is going to be images. So there has to be some rearrangement of the input instead of thinking of input as like numbers one below the other, like a vector. Image naturally has numbers, next to each other, below each other, and so on. There's natural orientation. So we'll change the input, okay, to look like a square or not square, but a rectangle. But also it will have depth, okay, generally because images also have, color images have channels, okay, 3 channels, for example, red, blue, and green. So we'll kind of have to change the input to a tensor. That's what I mean. A 3-dimensional array is a tensor, a 2-dimensional array is a matrix, 1-dimensional array is a vector, okay. So we'll have 3-dimensional array at the input, okay. So that's something with the depth. We'll also change, we'll not change, we'll not worry about linear, sorry, what is it called? Feed forward layers like this, because whether they are arranged in whether the neurons are one below the other or next to each other, it's the same. The layer's objective is to just have one neuron which is connected to everything else before it, make an inner product, apply nonlinearity, and send it forward. Whether you arrange the neurons one below the other, one next to each other, doesn't matter. Okay, they all are supposed to do exactly the same type of computation. Look at everything is which is coming into them, multiply, inner product, and so forth, right? So we're not worried about rearranging this. We can rearrange it, but it's kind of inconsequential, and we'll see that in a second. The important thing is we'll try to kind of use this because we have a tensor view here. We'll also first try to define the con layer in terms of at the layer level, and then look at what individual neurons do. Okay, so here's an example. In fact, this is the data set you will use in assignment 2. Okay, So CIFAR10 is a 10 class data set where there are really small images, 32 cross 32 pixels, but already they give you a sense of like if you multiply 30 times 30 is already 900 times 3, right? So 2700. So 2700 coordinates already, right? Or 3000 coordinates, let's say, already if you just vectorize it. But we don't want to vectorize it and pass. We can vectorize things and pass it through a feed-forward network. And in fact, assignment 1, you'll be doing that with MNIST, Gaussian MNIST. But here we want to kind of retain that shape. So that's the data set. And the idea of a network which has conv layers. So a network which has conv layers is called a convolutional neural network. So it could have other layers as well. It could have a fully connected layer or a feed-forward layer. Fully connected layer and feed-forward layer, by the way, are synonyms. They're just the same. Fully connected, it's exactly because each neuron is connected to everything else before it. Okay, every input before it. Now, in the CNN architecture, or in general, a model which has layers, but some layers are convolution layers. The right way to think about this layered architecture is to think in terms of tensors being processed from one stage to the other. So layers or some weights or parameters of this network process a tensor to another tensor to another tensor to another tensor to finally another final tensor. The final tensor is going to be exactly your score vector. So although it's a score vector, I'm calling it a tensor, but it's a tensor with depth 1 or width 1 or something. So even if it's 10 classes, you can just think of it as like a long cuboid. Okay, so everything now you need to think in terms of having a depth. So here's here's a point of view on the right side, which doesn't change anything from the left side. Okay, left side was a feed-forward neural network. Right side is also feed-forward neural network. Why? Because if you look at the right side, it looks like so just think of this depth as 1. Okay, so although there is a depth here for each layer, the depth is 1. And this, for example, I'm looking at this where the 4 green lines are intersecting. Think of that as 1 neuron's output. Okay, depth is 1, so of course there's no number before after. It's basically a matrix. Okay, this thing is a matrix. Okay, although I've arranged it in a matrix form, I can vectorize it, and there's no it's just a redundant interpretation here. This number here, this neuron's output, depends on all the inputs from before, and that's why I put a green green lines going to everything in the previous tensor, which has depth of 1. Okay, so all I'm trying to say in this slide is that the left hand side and right hand side are essentially the same. It's just a rearrangement of the neurons into a 2D 2D spatial arrangement rather than a one-dimensional vertical spatial arrangement. That's all. Is this kind of clear? So what we're going to do is now start thinking of tensors, right? So now input will have, so although I said input image here, just think of depth 1. So even if okay, let me make another point. Even if the input image has 3 layers, you can imagine this neuron, taking not just the numbers on the front, but numbers on the second slice or matrix, as well as the third slice matrix as well. So all the numbers, it doesn't matter how they're arranged. If it's a fully connected layer, it's going to look at all the numbers. Okay, whether they're arranged in a tensor like a 32 cross 32 cross 3, it doesn't matter. Just vectorize it into a 3000 dimensional vector and just pass it to each neuron. Okay, so input can have a depth, and still this is fine. What we're going to do is now, as I said, output will also be a tensor, and hopefully it's not going to be a depth of 1, but maybe 2 or 3 or higher depth, which means that neurons are now going to be placed not just next to each other as they are here, but there'll be neurons one behind the other, okay, or one in front of the other. Okay, so in an output tensor, if you think of output tensor having 2 layers, there's going to be 2 neurons. Okay, it's like 2 neuronal outputs. Okay, so every location in this tensor cell, like in this matrix or in this vector, every output there is a corresponding neuron. Okay, neuron just means that node which does the inner product plus bias and softmax or whatever. There's a plus ReLU or something. So here is the score vector, which has a depth of 10, let's say for CIFAR10, but width and height is just 1. Okay, why is it represented this way? We'll look at it later. Instead of why not vertical or something. So yeah, so the new idea is depth. Okay, so this I think I hide. Okay. Okay, so let's say, so instead of using this one hidden layer neural network, let's start talking about this two hidden layer neural network, just for a change of illustration. So let's say we had something like this with vertical placement of these neurons. Instead of that, we can now talk about, instead of that, but that is the same as representing things as squares like this, as I said, I just explained in the couple of slides ago. So nothing much changes here, right? Because all these hidden layers now still are tensors, but depth of one, which is like a degenerate depth. So depth of one tensor or three-dimensional tensor is literally a matrix, nothing else, right? It's just a matrix arrangement. So remember, every if it's a matrix, there is numbers next to each other, or numbers below each other. Those numbers are outputs of a corresponding neuron. Okay. Okay. So with that, let's now talk about depth. Now, what do we need is a tensor leading to another tensor and leading to a tensor. Maybe these tensors in between have depth, in the sense that depth is not just one. Okay, so which is like this way. So that means, like, if you kind of crack open one of these tensors, you need to have, there'll be cells, right? There'll be locations where there should be numbers. What I'm saying is, now the neurons are not just below and next to them, but there are also neurons behind or in front of them. That's all. That's all. So every place is a computed number. It's just that that number is the output of some neuron computation. Okay. Now each neuron, if you remember in the feed-forward case, each neuron has some weights associated with it. Similarly, here each neuron will have some weights associated with it. Okay. In particular, we'll see that it's a teaser, but we'll see that all the neurons in one depth slice, okay, one depth slice, which is like one matrix, will have the same weights associated with them. Okay, and those weights are exactly the filter weights. And we'll talk about, last time we were briefly talking about filters towards the end. So a single filter results in one slice, and another filter will result in another slice. You decide number of filters, like say I want 50 filters, then there will be 50 such slices, matrix slices. All these numbers. So essentially, like, each filter corresponds to is kind of determines the output for all these neurons in the same slice. Okay, that's the key idea. But we'll get to filters again in a second. But I wanted to give you like an intuition, because I used the filters idea last time towards the end. So is this clear? So depth just means like an arrangement of these numbers in addition to height and width, like one below.
At this point also, you cannot get transition from each neuron being connected to every other point.
Yeah, here you can think of neurons being connected to every other. So for now, but we'll now change that. Okay. Yeah. So even if we do this for, let's say, linear layer, for example, a fully connected layer, it's not going to change anything. So if a fully connected layer, whether you arrange the neurons one below the other, or like a matrix or a tensor, each neuron is connected to everything else before it. Yes, exactly. Yeah. Yeah. So before we get into the construction of that tensor output using a con layer, I want to just mention at the high level what other layers are available in such a CNN architecture description. Of course, the ones highlighted in blue are the ones which are new, and we're going to talk about them at length now. But the last one is fully connected layer, is exactly the fully connected layer. It's called a feed-forward network layer. Okay, is the same as before. So that's the one where you don't care about rearrange. You can rearrange, but it's all kind of redundant. Okay, so the next two slides are just talking about how to stack them. So here's an example where input can go to a con layer, and then a pool layer, then a fully connected layer, and then an output is generated. Like, so fully connected layer to output we have already seen several times. So there's nothing much going on. But each of these layers you kind of represent in terms of the tensors that they produce. Okay, so input is a tensor. If it passes through a con layer, there's an output which is potentially a tensor with some depth. That passes through a pool layer, that will also be a tensor with some depth. And after fully connected layer, there will also be a tensor with some depth. Okay? But the depth could be degenerate. Okay, fully connected layer, depths are generally degenerate. Yeah, so as I said, but although the name is a different name, at the end of the day, behind the scenes, there are neurons. I think I just mentioned it when I looked at the tensor. And the neuron computation is the same as fully connected computation, except that the weights are shared. As I said, all these neurons in one slice here, this slice, for example, the first slice that I'm using my mouse to show, this slice, they're all determined by the same weights. Okay, so that's the only difference. Otherwise, the neuron computation is the same. Inner product plus bias and non-linearity. Okay, so polling, as I said, it's like a shrinking of numbers. So if you had 10 numbers to start with, you want to have 5 numbers later. Or if you had 16 numbers to start with, you do 8 numbers as the output, and so on. So how do you reduce numbers? You can drop some numbers if you want. You can take averages, you can take max, min. Somehow you kind of get rid of some resolution, basically. Okay, and we'll look at that in using pictures in a second. And fully connected is, as usual, there's no, there's nothing new here. Okay, so yeah, so I'm just putting them together. This is how a block diagram looks like. Some layers have parameters, which is common when fully connected. Some layers may not have parameters, like pool may not have parameter. Of course, there's some design choice to say what is the definition of a pool layer, but otherwise you may not. So when I say some layers have parameters, these are parameters that are tunable. Like you want to find the gradient of the loss with respect to these parameters and then update them. Okay. Okay, so now let's actually talk about the con layer. And now step back from the layer view and let's talk about what constitutes what defines the con layer. Okay, so if somebody asks what defines the con layer, it's just a collection of filters. Okay, and what a collection or set of filters. And what is a filter? Filter is again a tensor. Just think of this tensor as like a Rubik's cube, like a small box. Small 3x3x3, for example, is the dimensionality of filter. And what is a filter? It's just a collection of weights. So con layer is also defined by a set of filters, which filters themselves are a collection of weights. Okay, so just think of the set of tensors, but each tensor, of course, has to have numbers in them. So that's the definition. That's the parameters that define a con layer. Okay. And what is a filter? It's just a linear function. So linear function, immediately you should think back, okay, what is a linear function? It's just a matrix, typically, okay, or a matrix plus a bias. So a filter is also a linear function, but it looks like a tensor. So we'll talk about how it is still a linear function in a second. And so since it's a linear function, it takes an input, something like a vector, or in our case, you'll see it's going to be a part of that input tensor, and then produces one number as an output. Okay, so a filter, again, if you want to think of function point of view, it has 3x3x3, let's say 27 numbers. Those numbers, they look, get multiplied with some smaller set of numbers in the input tensor, and then one number is produced. Okay, at one location, and then the filters are are sliding, and we'll see the sliding activity in a second. And so several numbers are produced. Okay. So that one number being produced is exactly this one number here. So for example, think of this circle here corresponds to one number that's produced by these by one filter multiplying with some part of the input. Okay, that's one neuron computation. Okay, and we'll come back to this.
The filter, as you said, same for the first section.
First section, yes, first slice. Let's call it depth slice. Yeah, this is the same filter weights. Those are 27 numbers being used for producing all these numbers, and then some other set of 27 numbers produce this set, and some other set produces this, and so on. Actually, there's an illustration in a second, but I'm jumping ahead. So let's take an example as 3x3x3 filter. So the filter depth is 3 here. So what do we do with a filter, right? So how do we get this, this slice that I've been using my mouse to show it? So how do we get this slice? We actually slide, which is the technical name is convolve. We slide the filter across the width and height of the input. Okay, the input is still a tensor, but we'll slide only on the face of that thing, and compute one scalar output. And here's an illustration where I have removed the depth. Okay, so if there was depth, I'll tell you what's going to happen. If there was no depth, let's say input has no depth, then let's say the input is represented by this green box, or at least represented by the bigger bold numbers. Okay, so that's the input. Let's say it's just zeros and ones. The filter weights, since I removed the depth, instead of 3x3x3, it's just 3x3x1. Okay, so that's just but the filter depth has to be similar as the input depth. So if the input doesn't have depth or depth of 1, then the filter also has the same depth. Okay, that's how you have to define it. And the filter, when I say sliding, you start with the top left, multiply element wise with the input, and then sum it up. Okay, so you see that only there are 4 cells where it's 1 times 1, and so that's why the output is 4. Now next computation, what you do is slide the filter by a predetermined amount. Okay, so here if you slide the filter by 1 unit to the right, then you will be focusing on this part of the input, do an element wise multiplication, add them up together, and that will produce a second number. Okay, Now, who decides how much to slide and all that? We'll briefly discuss it. It's just again predetermined. Okay, I mean, in the sense that you have to make a decision of how much to slide and all that. But that's how you get these numbers. So the second 3 cross 3 numbers produce the second number, and the last 3 cross 3 numbers produce the last number. And so there is some overlap, right? So the second set of numbers involves just one extra column of new numbers, but some 2 columns of previous numbers. Okay. Now, what happens when there is depth, right? So if this was not just the input was not just this matrix, but actually was a tensor with depth 2, then what you do is filter will also have depth of 2, okay, because input depth should be the same as the filter depth. You again do the same element-wise multiplication with the first phase of first slice of the filter with the first slice of the input, second slice of the filter with the second slice of the input. Okay, element-wise multiplication, add them up. Again, you add them up across the slices as well. Okay, so ultimately you have to produce only one number. You do all these element-wise multiplication, overall addition, compress all of them into one number and just return it. Okay, so that's what happens if there is depth.
So for this to work, the filter has to be significantly smaller than the input.
Yeah, filter has to be, yeah, think of the degenerate case. I mean, of course, filter is bigger than the input, then there is some choices you need to make. The worst case would be like filter is the same size as the input. Then you can't really slide, right? You just kind of matching them together, element-wise multiplication, and then producing an output. And that's actually exactly what a linear layer is. Okay, fully connected layer is. There is no sliding activity. there's essentially a filter defined by, there's only one filter with the size being exactly the input size. You can make that connection, right? Yeah. For those who did not make that connection, that's fine. Any questions? Yeah.
How do you use the weights on the filter?
That's what we learn. So just like the fully connected layer, there's going to be weights, right? We're learning using gradient of loss with those weights. Just like the con layer, as I said, is a collection of filters. Each filter is a bunch of weights. And so when we do a gradient, when we want to learn the parameters, we learn the parameters of the con layer, and which implies in learning the parameters of the filters. Yeah. So gradient descent again, but we'll not get into the details of deriving it by hand or anything. Software will do it for us, PyTorch or TensorFlow. Yeah. Yeah.
32 plus 3. That
Yeah.
is a grayscale single image.
It's a color image. Yeah. So actually, there's a quick example here. Let me come back to these slides in a second. Yeah. So let's look at filter operation again. So instead of 32 cross 32 cross 3, let's say the blue area is the actual image. It's just 5 cross 5. Okay. Instead of 5, it's 5 cross 5 cross 3.
That is a single image.
Is one image, yes. So the blue area, the top one is slice 1, second one is slice 2, and third one is slice cutoff, but the third one is the third slice. Okay. Think of this as this part is red, this part is corresponding to blue, and this part is corresponding to green. Okay. The numbers inside should be the pixel intensity of red, pixel intensity of blue. Ideally, here is just an illustration, right? So is the input clear? Okay. So what we are doing is some extra things. I'll come back to. So okay, I'll just mention it here. What we're doing is just enhancing the input with some extra zeros around it. Okay, so it's like if we had a matrix of 5 cross 5, we're just making it a matrix of 7 cross 7 by adding zeros on left, zeros on right, zeros on top, zeros on bottom. Okay. Once we do that, here's the filter operation, right? So there are 2 filters being shown here: filter W0, filter W1. So think of that con layer can have any number of filters. Let's say it has 2 filters. Okay. Let's focus on the second filter here, which is highlighted, because the first filter operation is the same. So if this is a filter with, let's say, current set of weights, of course, as he said, we're going to change these weights to learn them. But for now, let's say for simplicity of illustration, let's say these are the filter weights, 0, 1, -1, and so on. Then what do? You go to the top left, multiply element wise, okay, with this first slice with the first slice. Filter weights, this filter second slice with the second slices top left, and filters third slice with the third slice of the input top left. Okay, same area. So you multiply element wise. So 0 times 0, 1 times 0, -1 times 0, and so on. Okay, so you multiply element wise. Okay, you get a bunch of numbers. Add them up together. If you add them up together, for this slice you'll get some sum. For this slice also you get some sum, and here also you get some final summation, right? Now add them all of them together. Okay. Finally, whatever that number is, that's this number 1 here. Okay. So this is like really elaborate, getting into details of computation, but
are we reducing information here?
No, this is a linear transformation. So of course, any linear transformation from input to output, if it's think of linear transformations can reduce information. Yes. So here, it's not that we are trying to reduce information. Yeah, there's only one number from a bunch of input numbers, but then we're going to have a lot of such filters. Okay, let's say several filters, and then that's just here, right? So there's also overlap with, let's say, the second number here, 3, has an overlap with this information that was also used in first numbers computation. So yeah, there is a reduction number, and that's the purpose. We want to go from a rich input to eventually just a score. All the classification supervised learning is all about going from some huge dimensional input vector to saying what's the probability of first class, what's the probability, which is, let's say, three classes, 3 numbers. So there is always information being lost, right? But it has to be lost in the right way so that we can actually get what is the probability of each class. Yeah. Where is the what? Okay, so why is this? Okay, good question. So why is this not? So if you slide by 1, so this is the second, this is the third, this is the fourth, and this is the fifth. So if you slide by one, what is called stride? Okay, that's the parameter, and we'll see that. If you stride by 1, then if the input size is 5 cross 5, the output is also going to be 5 cross 5. Okay. The reason why it's 3 cross 3 is the stride is 2. No, it's going to be 5 cross 5 if the stride is 1 with this. Okay. In this illustration, the stride is 2, and that's why we're getting a 3 cross 3. And we'll go back to those slides and talk about that choice. Okay. Where is this? We were in this picture, and now let's brief quick comments on what filters are going to be small. I think we just saw that somebody asked like what happens if filter is huge. Filter depth has to be the same as input depth. We just discussed that because they have to multiply element wise to so depth has to be like the same. And as we slide F1 filter, we only get one 2D activation map, or it's called matrix basically. Okay, it's called a 2D activation map, and 2D explicitly says it's going to be a matrix. So one filter, one slice, or one matrix. Okay. And as he asked, okay, filter parameters are going to be learned during training. Okay, just like the weights of a fully connected layer also learned during training. Okay, by backprop, updating the weights and so on. And the intuition level is that these filters, the reason why we're using this terminology is because I think last time I was showing some grayscale image with some sharpen filter or blur filter and so on. There's that historical connection to signal processing based ideas of filtering. Okay, so in particular, also before deep learning, people used to create specific type of filters to detect certain types of feed patterns in the image. Okay, it's like colors, oriented edges, and things like that. So that's why I guess the name filter. So let's actually look at the neurons now. So as I said, one filter produces a whole slice. The slice is actually means that there is a neuronal output at each location of that slice or 2D activation map. So all these neurons are determined by the neurons computations are using the same filter weights. Okay, so there's weight sharing, and that's how we can get reduced parameters. Okay, and let's look at neurons just briefly. We kind of understand how it is, but we'll kind of get to the neuron perspective now. And in particular, each neuron, because the filter size is small and it's sliding over a region. So let's say in the top left, is only looking at the 3 cross 3 region. So that neuron, if you think of that one number, it's like a neuron output, but that neuron is only looking at a part of the input. Okay, so that's each neuron is only connected to a local spatial region of the input tensor. Okay, in the spatial side. So unlike the 4 green lines I had previously, when I reorganized the fully connected layer, where the 4 green lines were connecting the full input, here it's going to be only looking at a small part of the input. Okay. That's called the receptive field. Again, connections to neurons, biological neurons, and so on. But it's just called the receptive field. What is the extent to which the filter can see? So if the filter is large, then it can see a bigger part of the input. If the filter is like 3 cross 3, it can see a small part of the input. Right? That's yeah. So this is, I guess, an illustration. So this neuron here, determined by some filter, is only looking at this part of a 32 cross 30 cross 3 image. Let's say we are in the first con layer. The second neuron here behind it is determined by a completely different filter. Okay, but that filter we'll also need to have like the same dimensions, because if you want to have like a very consistent tensor here, otherwise the second filter has a different shape and it's striding in a different way, then you're going to get an output slice which is not going to be the same as the previous filters 2D activation map. So you want to have similar sizes. So these are, let's say these are five neurons. They're all determined by different filters, but they're all looking at the same region. Okay, so it's like some redundancy. So maybe some filter detects edges, some filter may detect colors, some filter may detect something else. That's the kind of the interpretation of these things. Okay. Is any questions here? Yeah.
So if I understand this correctly, so the motivation for this is originally if we talk about an image.
Yeah.
It was so huge that our original linear transformation cannot be done because
Yes.
it's a huge competition.
Yes.
What we're trying to do here with the filters is two things. A, we are of course applying some kind of transformation. Instead of a linear transformation, we are using some filter transformation.
Filters are also linear transformations, except that
in this case, we are talking about a linear transformation, but it's
yeah.
also helping us to reduce the dimensionality of the original matrix to
yes.
Layer by layer process. So the
no, you will reduce the dimension, but you're using less weights to do so. So if you have, let's say, 5 filters here, each filter is, let's say, 27 numbers, 3 cross 3 cross 3. So 27 times 5, right? 135 or whatever numbers. Whereas if each neuron was supposed to connect to all the input, then each neuron itself, the weights needed are about 3,000. Okay, so just 5 of them is 3,000 times 5 here, 15,000 here, but you can imagine there are many other neurons. So you have a huge blow up in the number of parameters, which is not the case here. Okay, so we are getting away with less number of parameters, but the transformations are all the same. Each neuron is exactly doing an inner product. Basically, we saw the filter operation is just element-wise multiplication, sum them up, and then pass through a nonlinearity. A nonlinearity I didn't mention, but yeah, we have to pass through a nonlinearity. Yeah.
So if an image has it's fully rich with information, what we're trying to do is capture some part of that information.
Yeah, piece by piece. Yeah.
And by one depth captures a part of that information, another depth.
Yeah, another filter could capture some part of the information, and so on. Okay. So the way, so there's local connectivity which is being explored. In an image, it cannot be completely random, right? So if there's an object, there is some local similarity, right? So if there's, let's say, an image of a cat, then patch by patch you will first learn something, and then that will be aggregated together to learn a little bit bigger region, and you'll see maybe there's a picture, if not. So if there's another con layer, that filter will actually look at the bigger region of the input. Okay, because although that filter is looking at a small region of its input, that input is determined by their own small regions. And so if you think of the receptive field of a con layer, which is like 5 layers down, it's actually looking at the whole input. Okay, and we'll get this intuition a little bit more later. Yeah. Yeah.
So when you say different filters, is it parameterized by different parameters?
Different parameters, yeah. I said the con layer is captured as a collection of filters. Let's say 10 filters. Then each filter will have its own. Is basically each filter is a tensor. You can think of, and that tensor will have a bunch of numbers. Those are the parameters, and they have to be trained.
In addition to filter, it also is determined by the places it traverses, right?
Yeah. So if you define a filter, let's say 3 cross 3 cross 3, you need to also say how much stride it is, and we'll see in the next slide. And I guess how much zero padding you need to have.
Okay. Yeah. Also, Professor, is it possible to get a operationalization of matrix dimensions in as if you can see, like from input to right, from input through con and to pooling and through output? Is it possible for us to see something?
Dimension choices?
How is it changing for each filter? How is it changing for each cell?
So filters you determine with the input as okay. There are a lot of things that you need to choose, right? Input. So what is this? Just like in the polygonal layer, you were choosing number of hidden units, for example. Here you need to choose that in the con layer. What are the choices? You need to say how many filters do I want? Okay, because the filter depth is fixed, but how many filters you want is up to your choice. The number of filters you choose determine the output tensor's depth. Okay, so the output tensor's depth is determined by number of filters. Output tensor's size, how much is the width and height, that's determined by how much zero padding you added and how much striding you want to do. Okay, so we'll just kind of come back to that in a second. So yeah.
So does the depth slice of the set of filters relate to this depth, like the input or depth of it?
So depth of the input, let's say it's 3 here, which means the filter depth has to be 3. Okay, but the output depth, output times depth, is the number of filters.
Okay.
Okay, each filter will have the same depth as the input, but if you choose 5 filters, then the output depth will be 5. Yeah. So let's talk about these other choices that you're asking, which determine the sizes of the matrices, right? So the layer depth, the con layer depth, is the number of filters, which literally says how deep that output tensor is going to be, number of filters. Now stride is how much should the filter should move spatially. Okay, so stride is 1. That means exactly 1 column is removed from the left side, and you get 1 more column on the right side. Stride is 2. Then you jump 2 pixels to the right. Okay, and zero padding is exactly how many zeros to add at the top, bottom, left, right. Okay, so if you add the typically 1 or 2. Okay, so those pretty much determine what would be your output tensors depth and width and height.
Okay. Why do we add zero padding?
If there is some information that is at the edges that you want to really, I mean, it's just a heuristic. I mean, why zeros and why not something else and so on. It's just a heuristic so that in case there is some numbers, like this pattern of numbers 1 1 0 1 1 1 0 1, for example, without zero padding, you're not able to go up here and maybe pick up some signal that you want to detect. It's just for it's just some empirical choice.
Like if a picture had a border, then we can detect the border. Something like that.
Picture has a border may not be useful for predicting something, but like if there's a signal at the edge, so think of not 3x3 filter, let's say a bigger filter, then maybe it has to be rightly aligned. So like think of filter as a stencil, right? So let's say the filter weights are such that exactly if there is a particular symbol at somewhere in the image, it has a high number output. So that original, so think of like stencil type of an operation, right? It has to exactly align, and maybe because you did not put zero padding, it hasn't, there's no chance to align in that corner of the image, or the edges around the image. It's just if you want to hedge against something, then you can add something like this. You can also skip it. It's not. You can check its effect if you want. Yeah, basically this parameter sharing idea is basically a filter detects, let's say, colors or edges is useful in one region of the input, then it's also useful in other regions. That's why we are sliding. Okay, it's like hey, detect the color or detect the certain pattern in the image. Doesn't matter where the pattern is. You slide through the whole thing, and if it's somewhere, then the filter is gonna have some of these outputs high. Okay, and we already saw this filter generates one such green slice 2D activation map. So I hope this is a little bit clearer in terms of dimensionality of matrices, but you can't predetermine. You can always start with some numbers and see what type of filter I should have, so have the same size of tensors. That's all flexible. You need to choose.
So if there is a 3x3 block that a filter has already traversed, is it possible for another filter to traverse? Will it be possible?
So what do you mean? So the input is 3x3?
Yes. So let's say in a 3x3, if we are traversing, let's say 2x2, the size of the filter is 2x2 dimension.
Yes.
And it has traversed one block.
Yes.
And we have another filter, let's say.
That's operation you have to think of it independently, because one filter's operation, you do it, get a 2D slice, and then forget about this filter. Only talk about the next filter. Again, the same input.
What about the inputs?
Same input. Input remains the same. So yeah, they are basically looking at the same numbers, and they're maybe traversing, as you said, striding around the same way. Okay, it's just that the filter weights are different. That's why the output could be different. If all the filters are the same weight, then each of these green slices will have the same numbers. Okay. Yeah. Depth of the filter, you mean, or depth of the number of filters we use?
You might end up getting more features.
Yeah, I mean, I don't know off the top of my head. There are some choices that have been made for the popular architectures which did well in the ImageNet recognition challenge and so on. Yeah, it's all trial and error. A lot of things are trial and error here, by the way. It's all engineered models, right? You need to define the model. Now, how many hidden layers, how many neurons per layer, how many filters, how much stride, how much this. They're all like, a lot of them is trial and error. There's no rule of thumb. I mean, there could be rules of thumb that people have figured out, but it's just rules of thumb. No, it's all nonlinear curve fitting process, if you want to think of it that way. Okay, so I think we already discussed the number of parameters being reduced. It's just a number of filter, layer depth, which is number of filters times the filter size plus one, because there's also bias that I did not mention, but it's very similar to the linear layer bias. Okay, you do a matrix vector multiplication plus one, sorry, a neuron, which each will have a little bit of offset. So that offset is one additional parameter. Okay. Okay, so here's in the first lecture I mentioned there's a huge drop. There's a 10% absolute improvement in the top 5 error in ImageNet large scale visual recognition challenge. So that network actually had much bigger filters. Okay, it was 11 cross 11 filters. Okay, instead of 3 cross 3 that I'm illustrating before. But now the community has converged to 3 cross 3 as kind of a choice. So these are actually the filters that you can visualize, and that's because this is the first layer. And so the filter size is exactly the input depth size. So you can actually just plot them as I am show, because it's a 3 cross 3 and its depth is 3. Yeah, and so you can see, you can see that there are different patterns, but at that point, people had this intuition that okay, maybe they are detecting low level features like edges oriented in this way, that way, colors of certain types, and so on. So that was the this is the illustration for that. We already saw that example. So let's now switch gears. And that's pretty much everything that you wanted to know about the details of con layer. But in programming, you'll just call con2D with some parameters, and it'll actually just do the con operation, create the output tensor for you. Okay, either in TensorFlow / Keras or in PyTorch.
At every point, we are still doing matrix right?
Yes. So there's no tensor arithmetic today to say as such, because it's a linear function. Linear functions are just matrices. Okay, so yeah, it's not. It's not. There's nothing of a tensor arithmetic that we're going to do. Yeah, just linear functions after and then apply non-linearities like ReLU and so on. That's all. Yeah, the spatial view is just motivation to say, hey, images have this local structure, spatial invariance, and things like that. That's what we are exploiting. Otherwise, you can just
So, some kind of video or some animation where
we
start from an input layer.
There is one. There is one in a couple of slides. Okay, that's just to summarize or recap the whole thing. But we'll do. We'll come back and look at that visualization. But let's talk about pooling layer for now, which is actually much simpler than the con layer. What we just want to do is whatever is the input tensor, we just want to reduce its width and height. Okay, so if the input tensor had whatever depth, doesn't matter, but it has a width and height of, let's say 8 cross 8, then we want to change it to, let's say 4 cross 4. So reduce the number of numbers basically. So if an 8 cross 8 matrix, for example, one slice of it, then you want to change it to a 4 cross 4 matrix. Okay, and so it does operate independently on each depth slice. So depth, is not kind of critical here. So how does it do it? So here is an example, I think from, in fact, the original AlexNet model. So if you had 224 cross 224, ignore the depth. 64 is not super important. 64 was because there were 64 filters probably in the previous con layer. It just becomes 112 cross 112. So what does it actually do? So if you had an activation, the slice had an activation like this, activation map, which you can look at as a grayscale image, it just becomes coarser, right? It just reduces the number of numbers. And so here's an example of how to do pooling with one particular operation called max pooling. You can do average pooling, you can do other things, any other choice you want to do. Max pooling just means, hey, pick the max out of, max pooling with 2 cross 2. Here also we're using the word filters, but just means that max pooling with the 2 cross 2 filters unstride 2 just means bunch of 4 numbers, 4 numbers next to each other together. Okay, which just means like 1 4, 1 1 5 6 is one of the slices of the input tensor. You just take the max and then that's the output. And unstride 2 just means, hey, now jump two columns to the right and so on. Okay, so it's basically then max of these 4 is 8, the max of these 4 is 3, and so on. Okay, so it's just reducing and taking a max of regions in your input matrix. Okay, so this is something that people use. And why did they want it? Because it reduces the number of numbers, and you kind of want it. Eventually, you're gonna, if you use a fully connected layer, and you know that for the final softmax or final probability computations, coarse computation, you do want a fully connected layer because you don't want tensor type of view there. so this reduction in the number of parameters, these numbers help, because now if there's going to be connected a fully connected layer, there's only going to be 4 weights per neuron. Previously, it's going to be 16 weights per neuron, right? So you reduce by a factor of 4.
You have parameters when you get it.
There are no parameters here currently, because it's just saying take the maximum out of 4. So that function doesn't have any parameters.
So from on to pool, we don't have any data.
Pool layer doesn't have any learning, so nothing, no parameter to learn. Con certainly has the filters, and filter weights have to be learned. Yeah. By the way, this is all just one particular journey through an architecture definition. People have tried 100 different variations of pooling, and they could have parameters. Okay, in the literature, if you see something. So this is not the only way to define a pool layer and con layer, but this is the canonical architecture that we're looking at.
So how do we know which pooling is the best? Because the other
Again, all these choices you have to empirically try, and so what we are studying is actually the Pareto frontier of like good design choices. And in fact, we'll see today later on dropout and so on. They're all design engineering ideas or basically empirical ideas that have some intuition but also do well in practice. Yeah. So polygonal layer, we'll probably skip that because it's just a regular polygonal layer. So this is I don't know if this link still works, but this was a link which is doing CNN, like getting a sense of matrix dimensions and so on in the browser itself. But let's actually look at a different animation. Okay? So that animation link is in the next slide deck. So yeah, so basically what we want to exploit is this hierarchy of features, in the sense that each filter has a receptive field which is looking at a small region typically. But let's say there are 2 or 3 con layers tied, one after the other. Then the filter in that, let's say, third con layer has actually a much bigger receptive field, essentially because it's getting information from a bigger part of the input image, okay, because it's few layers down. Okay? Although its own receptive field could be really small, like it could be still a 3x3 filter, but then that input it's taking is from other receptive fields, and they are also spread out like exponentially growing receptive fields. So that's hierarchy of features. So you start with small features like detecting edges, orientations, colors, and you kind of compose them into bigger features. And we'll see that illustration in the next slide deck when we try to diagnose a trained model. Locality is one big thing, that there is the spatial locality. That's why we're sliding. And so locality is one big thing, and then the last one is spatial invariance. That the actual pattern, it could be anywhere, and that's why we're sliding with the same filter everywhere. Okay. Yeah. So with that, let me actually switch over to the next deck. And actually, let me. Yeah. I don't know if this is a good browser or not. Maybe we should use a different browser. Okay, let's see if this works. So this is just a recap of whatever we've seen so far. So this is supposed to be having two. Okay, so what is going on here, right? So actually, let me. Okay, that's gone. So what you're seeing is an input. Okay, it's a grayscale image here. That's the input, and then you can see 1, 2, 3, 4, 5, 6 filters. Okay, so there's 6 filters, and so you can see so if you look at one filters, so each one is producing a 2D activation map. Okay, just think of the output tensor being depth 6. Okay, and these filters are actually, I guess, 3x3 probably. So these filters, you can see that if I'm asking for, hey, how did this output come? Then it's saying, hey, the output is because that filter was looking at that region. Okay, so each cell here is a neuronal output, but it's produced by the same filter weights. So all these, like this slice, this output slice is produced by the same filter weights. Okay, and so there's 6 such filters, and that's why you got 6 such outputs. Okay, 6 such 2D slices. So you can combine them. You can think of it as tensor. Now the next one is what's going on is the pooling. Okay, so it's is exactly max pooling. So I think it's max pooling, but basically shrinking in the dimension 2 cross, like if like this thing was 32 cross 32, then this will be 16 cross 16. Okay, so that's pooling. So con and pooling operation. Okay, you can see what 4 numbers combined together to form one of these numbers. I mean, it's just for illustration. Okay, it's not. They're trying to draw that, but and then from here there is actually many more filters. 1, 2, 3, 4, 5. I don't know how many filters there are, but now you can see that because they are so the connections are not good. But let's focus on one of these. So I don't know how many filters there are, but you can count them. So each filter here, so this output, this whole block was produced by one filter weight, one set of filter weights and one filter. To produce that number, you should look at all these 6 inputs. Okay, right now it's only showing as if it's connected only 4, but you should have lines over there as well. So that output, wherever my cursor is one 2D activation slice produced by one filter. Okay, at that level. So there is a second con layer that has 1, 2, 3, 4, 5, 6, 9, 12, 16 filters. Okay, so that con layer, so this output, wherever my cursor is, that horizontal line has a output depth, tensor depth of 16. Okay, and width and height you can think of the same. So let's say it's 3 cross 3 filters with stride 1 and 0 padding 1 or something. So that's exactly the same output. So it's 16 width and height, 16 cross 16 width and height, and depth is so the filter depth is 6, and the number of filters is 20. Okay, it's actually not 16. I mean, if you really count it, you can get the dimensions. But and then again, what is it called, a max pool operation. Okay, so you shrink down the number of numbers, and then now let's talk about fully connected layers. Okay, so there are actually 2 fully connected layers that we are going to employ. The first one is this fully connected layer. So every neuron there has to be connected to every number that's input to it. It doesn't matter whether tensor has certain shape or not. Okay, you can reshape it if you want, or vectorize it if you want. So each neuron has to be connected to all of them. Okay, and that's generally one of the densest layers in a CNN architecture. The number of weights in that layer is generally the highest. Okay, once you have that, next another one and one more fully connected layer. Okay, so each neuron there is connected to every neuron, every output from before. Now we are already in vector land, so this should be like your usual fully connected layer. And then finally the scores, again the output layer to the previous fully connected layer. Okay, so we have 10 scores here to detect what class it is. So you can see that it does detect that it's the class number 3, yeah, which is highlighted. So the intensity highlights the strength of that output. Okay, lighter color means, I guess, higher value. So is this I guess a good recap. Any questions here?
Sorry. If we not use the point layer, would that affect the accuracy of the model or the time it takes to compute?
If you don't use which layer?
We not add a point layer.
These fully connected layers, these 2?
No, the point layer.
Oh, pooling layer. Yeah, if you don't have the pooling layer here, then this fully connected layer will have 4 times more number of parameters per neuron, which is okay. So 4 times more number of weights. It may not affect the accuracy. So in the sense, if you have more weights, there's more chances to tune. Okay, so at least in sample performance, as in training error performance, could be even smaller. I mean, in the sense that error could be smaller, but doing that multiplication and keeping those weights and updating them is going to be expensive. Yeah. So you can skip pooling and see if, as long as you have a good beefy computer or GPU, then you can kind of skip pooling and you'll probably not be affected in terms of accuracy. Yeah, but you may overfit. That's the issue. Okay, so actually let me. So this slide deck actually has these 3 topics. So what I'm going to do is there's also one more topic, which is the recap of CNNs, but we will not do that because we just went through CNNs. We'll directly start with visualizing CNNs, which is more about, hey, if you already have trained a CNN, how do you understand that, what's going on with the weights, is it doing something correct or not? Okay, and the objective of that, this step is to really define one word. Okay, one important terminology or phrase is called an image embedding. Okay, and we'll talk about embeddings next lecture, word embeddings. So which is like vector representations of words next lecture. Here we're going to get vector representations of an image, which is which is kind of understandable, right? So image itself was a tensor, it's like 3 cross, so 30 cross 30 cross 3. But eventually we want to have a vector representation of that image, which could be like 10 cross 1. Okay, so that 10 cross 1 vector is like a representation of that, which captures a lot of information about that image, so that you can, it is as if those image embeddings can themselves be used in like a classification problem instead of the original image. So it's like feature encoding or feature engineering essentially. Okay, and that's what you can think of CNNs as doing, like doing feature engineering, so that like the last or the second last fully connected layer is producing that vector. Okay, where once you have that vector, it literally is just doing linear classification or feed-forward network or whatever, right? So that's the first part. The second part is transfer learning. As I said, when you have a pre-trained CNN, you kind of change the weights slightly. There are a couple of straightforward ideas there of how to change those weights. So we'll look at that. And then look at a few ideas that, as I said, these are empirical ideas that seem to have helped with deep networks training and improving the stability of the training process, which hopefully gets you good, stable models that do well both on training and test. And so those are that's the last bucket. Okay, so let's start with the first one. Let me skip these. Yeah. So all these deep neural networks, they're generally like collection of weights, right? So whether it's fully connected feed-forward networks or con networks. And there's a lot of non-interpretability because you cannot interpret the weights themselves like how you do in a linear model. Okay, or even decision tree, for example, is a really good interpretable model. But the moment you go to random forest, you have to choose methods like what is it called, partial plots or feature importance scores and so on, right? So you're kind of losing interpretability. Here also we have kind of no interpretability because each filter can have some weights, and how do you interpret them? It's unclear, right? We will not, in fact, that criticism is still valid. It's not like we can interpret each filter's weight or any particular, neurons, corresponding parameter easily. But we'll look at a few attempts. Okay. So those attempts are just partial attempts to kind of understand that your model, the CNN, is actually doing something. It has learned something. Okay, that's at the minimum. And maybe beyond that, you want to understand why is its accuracy not good for certain types of images, or why is its overall accuracy some value and not some other value, and so on. Okay. So so first two attempts are just trying to visualize what we have. Okay, so which is what if we can visualize the activations of which are the outputs of these networks at every. So activations are just outputs of hidden layers, right? Output of layers. Okay. So what if we can just visualize the activation? Okay, which is, so what are we trying to show here in the left hand side is the activation of about 6 times, I guess 36 filters. So activations of 36 filters. Okay, each one is producing a 2D slice when the input was an image of a cat. Okay, so cat image was an input, and then you see the activation. So activation, remember, it's a matrix, so you can just visualize them as a IM show with IM show or something like that. So you're looking at activations. Okay, similarly, you can look at activations at any depth. Okay, it's just that each slice you can just visualize it. The problem is, I mean, what do you gain by doing this, right? So the point is, let's say you had one image. Okay. Instead of that, let's say you have 1,000 images, or let's say 10,000 images in your training data. You can look at all the activation matrices and look at the activation statistics at each location. Okay, which is, for example, like for the cat, it's not for the cat, but let's say this is just showing for one image. But in general, you can look at, hey, in this filter. This block this active slice is corresponding to some filter. Does it even activate at all, right? So if the filter's output is always 0, okay, given all my training data, which means that kind of is a useless filter in the sense that either the nonlinearity is such that all the numbers input to the nonlinearity are like negative. Let's say it's a relative nonlinearity, so that the output is always 0, or there's some bug like that. Okay, so that's what you can figure out by just trying to get some activation stats like this. Okay. What's it?
Can you repeat that, the last one?
Like I'm just saying that, for example, think of this filter, right? So this filter where the cursor is. So let's say for the cat image, it looks like all the outputs are 0 for that filter. Okay. If you pass all the input images and still this thing is always dark, as in always 0, that probably means that the filter is not effective, right? I mean, it's not even doing anything. It's always.
Who tracks this activation?
We have to track it. So this is all diagnosing once. Okay, so just a larger context is that if you already have a trained model with already, you think the weights are good, you have good, decent prediction accuracy and all that. Now you're trying to figure out like, are there still any issues with the model? Okay, so weights are fixed. Now you're just trying to say, hey, I have training data. What else can I do? I can just pass the training data and now start looking at the intermediate computations, and that's what this is, right? Or you can say, hey, I don't want to look at intermediate computations. Let me try to visualize the filters themselves. Okay, but there's a problem with that, which is that at the first con layer, because the image is like depth 3, you can visualize them, and you can potentially have an interpretation like, hey, they're detecting edges or orientations and things like that. Okay. But the moment you go up, let's say even second con layer, the input is not, input is going to be whatever this number of, depth is. Input is no more an image, right? So what you could do is just look at slices, just like again, but, you look at the filter weights themselves as images. Okay. So filter, could have some depth in filter depth, which is whatever is the number of, outputs here. But each filter you can think of as it's a tensor. It has a number of weights in each slice of its sensor. You can just visualize that as well, and that's what's being shown here. These are just to show that maybe some filters have weights which are like maybe don't have any pattern. Okay, it's hard to do anything with these weights, but this is an attempt. At least at the first layer, you can see that if you haven't converged to something like this, which are just really low-level feature detections, basically, then your network is probably not going to detect anything interesting. Okay, typically, irrespective of what you're doing in the first layer, if the first layer is con layer, you typically want to get some patterns like this, okay, edges, orientations, and colors, and so on. So you can't basically get too far with weights unless you do something more esoteric. So now let's look at some bigger hammers. Okay, so one hammer is something that we already know from from some previous courses, which is dimensionality reduction, right? So what do? We have the input image, and then the output is the score vector, right? But instead of looking at a score vector, what we're going to do is look at the activations, or what is this called? The activations from the previous fully connected layer. Okay, so I think we have, yeah, basically instead of looking at the scores for that input image 3, you just look at this vector. Okay, this really large vector, long vector. Okay, so whatever those collection of numbers are, that's this H here. Okay. Let's say this also after softmax operation. So this A, this A here, or basically max of 0, that H. So that activation A can be considered as a vector representation of this image. Okay, and this is what we call as the image embedding. Okay, the vector representation of the image. Why is that? Because it seems to have all the information so as to get to the right class with just one linear transformation, right? If you think about it from the diagram. So what you do is that now you think of your problem as like a collection of vectors, and you want to say, hey, I want to understand whether similar vectors or similar images go to the same lower dimension. And so you kind of embed or reduce the dimensionality of these A vectors. Okay, let's say there are 1024 such coordinates in the A vector, so 1224 dimensional. From there, you can try to get to all the way down to 2-dimensional, 3 dimensions, and then see are the distance properties preserved. Okay, by which I mean these vectors are backed by images. Images are interpretable by humans, right? So we can see, hey, cat image, another cat image, they have these 2 vectors. By just looking at the vectors, we can't make out anything because they're not interpretable. But if we put the images, these 2 vectors embedded down, projected down to 2 dimensions, maybe the cat image related vectors, the 2-dimensional projected down vectors, they should be close compared to cat versus a house, for example. Okay, so here's a, this is a not very useful in a slide, but basically this is the projected down plot in 2 dimensions, where instead of showing the 2D point, the 2-dimensional vector for each image, we are actually replaced the image itself. So that's why, what you should think of is that you had these, let's say 1024 dimensional vectors or 4096 dimensional vectors, I think in this model's case. he just projected all of them into 2 dimensions. So the bunch of points in 2D. Instead of plotting just a point, you replace the point with the image, its image that corresponds to it. Okay, and also stylize it so that it looks like one next to the other and so on. So what you see is, for example, the embeddings for, let's say, sceneries. Let's see here, this grass, and I think it's a outdoors photographs. Seems like that. They're all clustered here versus some other objects here, and so on. Okay, some aircrafts over here and so on. So it seems like these image embeddings are reasonably correct in higher dimension. So you're just making that judgment based on the 2-dimensional projection here. Okay. Yeah.
So basically, what we're doing is like for a 10-class classification, we are saying like for number 1 to 10, we had 10 different scores.
Yeah.
And we knew that the final output score was this. That was the highest score, and it corresponded to 3. So something.
Yeah. Here the high score is this.
Yeah,
corresponding to 3. That's
corresponding to 3.
Yeah.
Something like this we are doing here, but what we are doing is all those collection of images
Yeah.
should have near about the same scores. And when you project,
no, we're not looking at the score vector at all, right? So we are projecting these vectors. This one before the final score vector. So this vector should have all the information regarding the image 3. Well, so that this vector versus another vector which corresponds, let's say, image with number 7. Those 2 vectors, which will, like, say 100 dimensions here or 100 dimensions there. Those 2 should be such that their linear transformations should give a high for 3 and a high for 7 respectively. And so those 2 vectors, if they projected down, they should not be close to each other. Okay. Whereas a slightly different 3 should have this vector such that if it projected down, it should be close to the previous 3. So it's like similarity. It's like clustering of these vectors, basically.
So after projecting it down, we show the images, not the vectors.
I mean, yeah, because vectors are not interpretable. Then I mean, the 2-dimensional vectors is a point, in a 2D plane. But looking at them, so it's just for interpretation that, hey, we got the airplanes at the right spot. We got the maybe the dogs at the right spot and so on. Like this is just one way to kind of get a sense that, hey, your image classifier is at least putting the right things, has the right embeddings. Okay.
So how is this different from, say, grouping the images that have the same score or similar scores together?
Grouping the images with the similar scores.
Not scores, categories. The prediction categories.
Oh yeah, we'll look at that as well. No, I mean, it's different, right? It's only looking at the embeddings, not the scores, because scores there's another linear transformation going on, right? Whether you look at this, I mean, we'll look at the scores as well. It's not like we're going to skip out that as not a good idea or not. It is also an approach. Yeah. Okay, so and before we get to the scores one, let's talk about another interesting idea, which is occlusion. Okay, so it makes sense for images, which is you want to figure out which part of the image is actually leading to the classification to be of that class. Okay, so what you do is actually plot a matrix. Okay, so if an image is of some size, 100 cross 100, then you also make another plot, basically a matrix where each cell is a probability of belonging to the target class. So let's say the original image is of a dog. Okay, then what we're going to do is plot a 2D, maybe the same 100 cross 100 size, where the first pixel is saying what's the probability of this image being dog. Second pixel is also saying what's the probability of this image being a dog. But the difference is going to be that we're going to occlude the original image and then try to pass it through the network and then try to say what is the probability of this being a dog. So let me show that by example. Oh, sorry, I think we lost the full screen. So let's just focus on the left-hand side. Okay, there's a lot going on in this picture. So these 3 pictures. So let's only focus on the left one first. So what is going on? So here's an input image, right? So what I'm saying is, given that input image, we're gonna instead of passing it directly through the CNN, we're gonna always occlude parts of it. Occlude just means like delete a part of it, like this graying of this region over here. Okay, so we're gonna do that. But where all can we occlude? We can occlude from anywhere, right? Just like a filter, we can slide the occlusion from top left all the way to bottom right. Okay, so each occlusion leads to one number here. What is that number? That's just the number, which is we know that this should be a dog. So we are saying, hey, in the dog score, what is the probability of the score being high, or basically what is the probability of this image being classified as a dog? Okay, so that's one number at the top left if the occlusion is the top left. Occlusion now slide it to the right, slightly to the right. Again, find what is the probability of this being a dog. So you can see that if I'm doing this gray thing over here, it's just saying that the probability of dog is high. Okay, red means high and blue means low. Okay, in the bottom figure. So you can see that the probability of dog doesn't change if I'm occluding like the background, some part of it. Okay, it's still high. Red means high. But if you actually occlude its face, you can see that, you know, over here, you're basically saying, hey, it's not, the probability of dog is going down to 0, blue, or basically 0. Okay, it's just a way to understand, hey, for this image, which part of the image is actually signaling that this is a dog. Okay, that's some post hoc stuff that you can do. Is that clear? Again, similarly for this car thing here, it's saying the true label is car wheel. So if you occlude the wheel itself, the probability of you saying it's a wheel is going to go down to 0. But if you occlude other parts like, you know, this, like some corners, it still says it's, it's red in the sense it doesn't influence. But you can see that it's also picking up some other parts. So if you occlude this area, it's still saying that it's not, it's saying that it's probably a car wheel is going to go down, which is not correct, right? So this is, for example, an issue. Yeah.
Can we have an analogy like in terms of, say, when you're doing random forest with variable importance? So like, we identify which features are critical to identify, or for classifying something. Something like that where.
Feature importance is a model diagnostic tool. So you already have a trained model. You're using feature importance to get a sense of which features were most used while doing splitting. Here, it's more at the data level. So in the data of a certain class, let's say these dogs, which part of the image is kind of most indicative of that class. Okay. So in random forest case, if you really want the exact analogy, it's like I have an input for which the random forest classifier is saying, hey, class 1. If I now in that input vector suddenly change the numbers to zeros in like the first 2 coordinates, does it still say class 1? In the next 2 coordinates, it still says class 1 and so on. If you really want that very literal analogy. But for vectors, it doesn't make sense, right? Like setting age to 0 or income to 0 or something else to 0 in a column, it makes sense. And you can probably do that even for tabular situation if it makes sense for that context. Okay. Any questions here? This is an interesting technique, right? I mean, this was not like very obvious, but interesting idea nonetheless. Okay, so there are 2 more. So the next one before we get to scores is actually synthesize images. You already have a trained model. Now you say, hey, I have this model, and let's say I want to say the class. Let's say there's a coordinate corresponding to dogs. Okay, let's say cliff dwelling. Okay, some nature, scenic photo. Okay, so let's say that class. Now you want to say, hey, the model is fixed, model weights are fixed. I want that coordinate, that score to be the highest. What should be the input that gives me the highest score? So you're saying, you're asking a finding, like a search question, right? So give me what is the best input that I can give, given this fixed model, such that that coordinate score will be the highest among all the 1,000 scores, for example, for ImageNet, or whatever 10 scores for them, right? So how do you, so this is a search problem, or basically an optimization problem. What you're optimizing over is not weights. You're optimizing over input. What is the input? It's a 3D tensor, right? It's like 32 cross 32 cross 3. You want to find the best 32 cross 32 cross 3 pixel values such that a particular coordinate is the highest. Okay? That's called synthesizing images. In general, it's not easy, and that's why you see very blurry stuff here. But you're supposed to see some patterns in there. But you need to, if you do handhold quite a bit of this optimization or search procedure, like you need to start with some natural image priors, which means the starting point should not be completely random input, but maybe start with almost something which looks like a natural image. Then it may be converging to the image which triggers that particular, which produces the highest score, not just at the score level. So for example, here, right? So what's the image which, let's say there's a coordinate which corresponds to goose, right? What is the image that produces the highest score for the goose coordinate, right? So this is the image which produces that. It's not a natural looking image, okay? But it does have all sorts of patterns, right? Bird-like patterns that kind of, apparently the network needs this type of patterns to produce the highest score there. Of course, if you pass a natural image of a goose, maybe it'll also classify that as goose, but this is the best image. Okay, and it's not very natural, but you can see that this is a way to understand whether you're doing something correct or not again. Okay. So you don't have to look at only the highest score. You can pick up any neuron. Ideally, for example, you can say, hey, I don't, so far we were asking what is the best input that gives me the highest score at let's say the third coordinate. You can also ask, hey, let me pick some random neuron here and say, for this neuron to be the highest, what should be the input? Okay, so you can do that for any neuron, right? So it doesn't have to be the last neuron. So here there's some attempts like layer 8, layer 7, layer 6. What is the best input for a certain pattern? And so the point of this slide is just to say that you go from like less complex patterns. Like at the bottom, you can see that there's some circular thing. You get more complex patterns triggering that neuron to be the highest score as you go up the layers. This is that feature aggregation I was talking about, like hierarchy of features, right? The bottommost ones will just detect edges or things like that, and then the later ones will detect some partial, image, partial object-like patterns. So but doing all this is kind of hard. I'm just kind of quickly mentioning these ideas to you guys. Next is what somebody suggested, which is the scores, right? Looking at scores. So you can just look at which images in my training data got the highest score, right? So if I have training data, I can just say, hey, for number 3, for the third class, which were the images which gave me the highest score? Which were the images which gave me the lowest score? In my training data, you can find that out, right? So, for example, you can say, hey, for number 3, these were the number 3 class-related images which gave the highest score. These were the number 3 class-related images which gave me the lowest score. What can I do to improve their scores? For example, are they very confusing in the sense that are they 3 is close to some other number, right? You can do those types of diagnoses. So this is just a picture of the same thing. It's just showing which images got the high scores. I think this doesn't even have to be done at the level of again the same final picture. You can just say, hey, like given this particular neuron, which images are the ones which are triggering it the most, giving high scores for that neuron's output versus some other images which are not. Okay. So what, why do this at the intermediate level is because maybe some neuron here is very important for picking up some signal. Like here, for example, I think this is some output of the pool layer. It's just picking up, all humans probably have to have the highest score after that dogs and after that inanimate objects, something like that. So you get, kind of dig deep into what's going on in your network, okay, different layers. That's I guess the higher level idea here. But this is something that a version of this is something that you will do in assignment 2 as well. So I think you should get used to being able to plot images at least, okay, which is an important minimum requirement if you want to work with images and vision. So there is a subpart in assignment 2 which requires you to plot those images which got the highest classification probability, for example, for let's say one of the 10 classes of CIFAR 10. So any questions? Let's probably take a break for 9 minutes, and resume at 5:20.
How do we decide on the architecture of CNF? Is there an empirical method?
No, I mean, we kind of, so that's a good question. So we kind of refer to there are some reference designs that have evolved over the past decade or two of research. We kind of start with the reference designs, and then if there's a really need for your particular application, like let's say you're not working with these general images, but let's say medical images, or if something is very specific to, let's say, e-commerce images, then there has to be some adaptation that needs to be done. Maybe they change the architecture, things like that. So, but there is no, I mean, there may be some recommendation from practitioners, but I wouldn't say there's a convergence of like exactly this is how you do it. So, okay, we lost 1 minute there, but let's resume at 8 in 8 minutes. Yeah.
Can you please go back to page 17?
Okay, 17. Yeah.
Yeah. For the image on the right, there is actually a dog, right? Or
yeah, this is a dog, right? Yeah, on the right, you mean? Oh, this one. Yeah. Sorry. Yeah.
there is a blue color, that be right?
This one?
Yeah. So for the color corresponding to the dog, it's actually blue, right?
No. If you want to say, if I occlude this region, it's just saying that the probability of this figure having a dog is 0. So blue means bad. Blue means bad and red means good. So if I occlude this person's face, it's like very confident that this figure is of a dog. Okay. If I close up this person's face, for example.
Yeah, what I mean, it should be the opposite actually.
No, if you occlude a dog, you should say probability of this image being a dog is not a dog, right? Come on. If I cover up the dog, there's no dog in that image. I should say the problem. Oh yeah. Occlude means cover. Like this if gray it out, then there's no more dog features or anything to pick up. Yeah. Okay. Okay, so let's resume. So we quickly spend some time on understanding, okay, there are some ways to kind of diagnose a pre-trained network, right? Pre-trained CNN, we saw a few approaches. Occlusion was like an interesting idea, but in general, dimension reduction is a standard idea to understand what, whether some, the right clusters have been formed and so on. So the next topic is actually kind of useful for many projects, which is called transfer learning, which is to use the strength of already trained models, which have been trained on high amount of computational resources, right? Like a lot of GPUs or a lot of data sets, corpus or whatever it is needed, and use them to tune them for the specific application that you have. Okay, like so let's look at what is the motivation, right? The motivation is that very few people train their networks from scratch, because it's not like the problems are extremely different from the problems that researchers or people who have made their models available have solved. Okay, so generally you don't even have to have a lot of data to use deep neural networks or kind of use such models, as long as some properties hold, which is that exactly this transfer property, which is that hopefully there is a open source model or a model that somebody else has developed, which can be reused at least partially for your application. As long as something like that can happen, then you don't really need much data to get a neural network performing decently well on your application. Okay. And there are two approaches. Both have somewhat straightforward procedures in terms of intuition. The first one is just feature extraction, and we have already seen feature extraction when we talked about getting image embeddings. Okay. And the second one is fine tuning, and which is actually more about, hey, let's continue training and slightly continue to change the weights of the network. Okay. So both of these, I guess, constitute loosely as transfer learning. Transfer learning in general in machine learning has much broader, I guess, context, but for us, transfer learning for deep learning models is kind of, these two are the approaches. Okay, there could be others, but let's focus on these. So transfer by feature extraction, as I said, is a straightforward idea, which says, okay, you get a pre-trained model like AlexNet from 2012 or VGG from 2014. Those are just the models that researchers in different universities / research labs developed and made the weights available, as well as the architecture. So you can just get the weights, which are numbers, the architecture definition you can define in PyTorch, and then upload the weights into that model, so that you have now a working model over which you can pass in any image and produce an output, right? So what you do is basically do exactly what we did for those embeddings and projection down to 2 dimensions. We kind of remove the last fully connected layer, which is the one which is generating the scores, right? You drop the one which is generating the scores. You just focus on the ones which was going to feed into the scores, or you could do 2 steps before as well. So kind of drop the last fully connected layer, focus on the outputs of the penultimate one, and just call them, as I said before, we just call them embeddings. And then with these embeddings, you can use any model. Okay, so these embeddings are now inputs instead of the original images. These vectors are the inputs for any model, like a random forest model or a loss aggregation model or anything like that. Okay. So when I said these embeddings are the input for any model, not the embeddings of you don't have the training data, you just have this model architecture where you chopped off the last fully connected layer. But you can get these embeddings for any input, right? So you get the embeddings for your images. Okay, so that's, I guess, I missed that part. So you get the embeddings for your images, and then from there onwards, you can use any shallow model or any other, including a simple, let's say 2 or 3 layer neural network to build your model. Okay, so what you gain by that is that all these previous steps, which were about picking the right features, picking the right spatial regions, and getting the right higher order features that we saw a couple of slides, a few slides ago, some images, right? So you can retain all that learning from previous corpus. Okay. So I mean, here's a picture just to show you the original AlexNet model had very similar like polling, con layer, and so on. And ultimately, their penultimate layer before they got to the 1,000 class image class classification situation was this 4096 dimensional activation vector. Okay, so that vector is the representation that you want to get for your own data as well. So everything else is fixed. The network is fixed. It was pre-trained already. You pass your set of images for your application and get this vector. Okay. Okay. So is that clear? So you just get that vector, and then once you get those vectors, you can use random forest, or you can use even a regular 2 or 3 layer feed-forward network to work on your specific application classification problem. Okay. Why am I suggesting random forest or 2 or 3 layers? Because let's assume that you don't have too much data. If you had too much data and a lot of compute, maybe you don't want to do transfer learning. You can probably spend effort on fully training something from scratch. Okay. Or you can do the second thing, which we're going to see now, which is transfer. Okay, this is not yet the next one. Transfer by fine tuning. So I guess this picture is exactly saying what I just said. Use a linear or nonlinear classifier, like a logic regression or a random forest or something like that. Okay, let's talk about transfer by fine tuning. So what are we going to do? We're going to instantiate the model, let's say in PyTorch. By the way, this is part of your assignment too. Okay, so a big part of your assignment too. And we have an example code in the examples folder as well. So what do? We instantiate the model. We have the original weights. Now we're going to continue doing gradient descent. Okay, but we're going to continue doing gradient descent. What data are we going to use? We're going to use our new data. Okay, so because the model was built on some data, let's say some original data, but we may not have access to the data. We may not be interested in doing well on that data. What we're interested in doing is in our data. Okay, which could be like an e-commerce setting, whereas the original one was, let's say, ImageNet. Then we start passing our e-commerce, let's say, product photographs, and then try to classify them as appliances versus, let's say, computers or something like that. Then, well, we can do that forward pass and backward, backprop, and change the weights of, the existing neural network. Okay. What we need to do is, of course, first change the last fully connected layer, because maybe the original ImageNet based model had 1,000 class classification, but in your case, maybe it's just a classification between appliances versus computers versus automobiles or something. It's a 3-class classification. So of course, the last fully connected layer will have to change. It only has to have 3 classes instead of 1,000. And maybe you can also start changing the weights of some previous layers. Okay, and generally you tend to go from the right hand side, which is like the last but one or last but two type of layers, and you don't tend to change the weights or tend to change the weights of these early layers. Okay, early layers, what they do is detect lower level patterns, so they will probably be similar across like images. So you basically kind of freeze these layers, freeze as in not set the gradient the learning rate to be 0, for example, or the step size to be 0 in the gradient descent formula, right? You can set them to 0 or some really low value so that these weights don't change, and these weights change when you actually train on your data. Okay, the ones in orange. So any questions about fine tuning? Yeah, we can even change all the weights if you want, but now what you do is like set the step sizes to be small, so that you want to capitalize on the fact that these weights are already at good values. Okay, if you didn't do any fine tuning, and if you just passed your original data, it does already somewhat decently in terms of classifying, let's say, automobiles versus appliances versus computers or something. Okay, if you have those classes. If not, of course, you'll change it and learn that final layer. But what I'm saying is that what you're trying to take advantage is that these weights are already at some good weight values, and you now want to slightly perturb them so that they adapt to your particular application. That's all.
So how do we decide at what point do we find it? At what point remains
It's again design choice. You try start from scratch and try to see. It's just a search procedure, just like any other search procedure or design choices you need to make. How much to backprop? So how many layers? What's the step sizes? There are all many choices you need to make, right?
The number of output classes are more than what is there in the original model. That's what cause the
No, it would not. I mean, in the sense that like there is no relation between the original pre-trained model and the new application that you have. If you have more classes, anyway, you're going to drop the original fully connected layer and create your own new one. But if you have more classes, maybe that previous weights that were learned may not be able to distinguish between those extra classes that you have. Okay, that that could be a weakness. Yeah, good point. Yeah, and I don't want to spend too much time on this slide. It's just showing what would happen if you have a pre-trained model. So think of so think of the original pipeline, the baseline, the benchmark pipeline as like image, do all sorts of feature engineering, and apply an SVM classifier. And instead of that, you kind of use a CNN pre-trained model, and then try to. So that's the yellow. I guess that's the pink one. So ignore many of the bars. Just focus on the green and the pink. Okay, forget the red and the blue for now. So it's just showing if you use CNN off the shelf and do all these types of related tasks, then you are not too worse off. Of course, you'll not be as good as the best let's say in this case non deep learning based model, but it's just showing that you are kind of competitive. And of course, if you do more, like further something called augmentation that we'll see next, then you may be doing even better. And if you specialize, you may be, of course, slightly doing better. So they're all very close to each other. You may say, hey, the bang per buck is not high, for example, for some business applications. But in some business applications, maybe it's useful to have 1 or 2% improvement is also significant. Yeah. Okay. So I wanted to briefly mention this because some of the tasks that mostly we've been focusing on classification. That's what I've been motivating from lecture 1. Classification just means there's an object in the image, has to be one of these 1,000 classes. Okay, for ImageNet classification, for example. But there are other problems like classification plus localization. Okay, where the output is not just the probability, it's not just a score for one of the classes, but the output is like 4 numbers, or 4 numbers, which is like the let's say coordinate 1, 2, 3, 4, or coordinates plus height and width. Okay, whatever it is. So now in your training data, you need to have not just the original image, what class it is, but you also need to have the reference, what I call bounding box. Okay, some 4 numbers will say, hey, here is the image, here is the object in that image. Okay, so if you have such training data, you can use that data to now create and a classifier which classifier, it's not really a classifier anymore, but classifier plus localizer, which any given new input, which will say, hey, it belongs to one of these classes, and here is the actual image. Okay, that's the second one. That extended to multiple potential classes in the same image is called object detection. And instance segmentation is really getting the boundary of each pixel. So which collection of pixels belongs to the particular class. Okay, that's even harder. So these are all different problems. Okay, different problems that related to vision. Some people have also, I think some people have tried to do like object detection. I mean, you can always get off-the-shelf models here, and so you can use some of these ideas here if you want to do in a project. You can also do classification, object classification, if you want. Okay, so yeah, I mean, just a quick minor comment on the projects. Again, you wanna do transfer learning, right? When you have a similar data set, and you have really small data, then feature extraction seems to be a good starting point. I mean, doesn't mean that you have to you can only do this. That's a good starting point. Okay. Or if you have small data but different data set, then certainly you should not go with deep learning, right? You should maybe start doing some shallow models or more traditional models. So a lot of data and the data set is pretty similar, then fine tuning is fine, because it's a good starting point, because because of similarity, you may already get some good bang per buck. But if you have a lot of data, but also not a good pre-trained model, then you have to in this case you have to either fine tune a lot or start from scratch. Okay, fine tune a lot basically means you kind of forget the previous weights anyway. If you do a lot of changing the weights. Okay. There are a lot of pre-trained models available, not just for vision, for NLP as well. We'll see several examples through the lectures. So I guess that's the key to the projects. If you are ambitious. If you wanna build on some existing models, then that's a good starting point. Okay, so here's an example of a somewhat deep network, right? So just to give you a sense of how to use. So this is a clean model from 2014. clean in the sense that what we discussed in the previous few slides about CNN architecture kind of conforms here, right? So it's image con 64, 64. I don't remember. It's like those many filters probably. Con pool, con pool, and so on. So it's very clean, like in terms of layers that we saw in the illustration before. But these days, the types of models that you see, for example, the model that we will use in assignment 2, it's called ResNet 18, I think. So it's a slightly different architecture. Okay, it's not exactly the CNN. It's not exactly the CNN architecture that we saw. It has some extra connections and so on. So those are innovations that people have figured out. Helps in better classification accuracies. Okay. But here you can see clearly you can drop the last few layers and do fine tuning or feature extraction based transfer learning. Okay. So any questions so far? Okay. So let's actually now look at some empirical ideas, or I wouldn't say empirical ideas, but ideas that have improved the training process for training these neural networks. Okay, improved the performance also. These are empirically validated. That's how they have surfaced as like popular approaches now. Community has a consensus on maybe these are the ones that you should try out to improve your modeling. Okay. The first one is related to just data, which is data augmentation, and that's the word that we used a little bit earlier. We're going to look at it. It's actually a very intuitive idea, data augmentation. And then there are three example ideas that we look at for modeling side, which is when you do the computation to train the weights. One is the initialization of the weights themselves. The second one is something called batch normalization, which is like an extra layer, but we'll see what it does. And dropout, okay, which is also another idea which is very similar to regularization. Okay, regularizing weights in a linear model, you would have add an L2 penalty or some sum of squares penalty for just the weights. Very similar idea in neural networks. Very similar motivation, but dropout is different, and we'll look at that. Okay. We'll just fix the optimization idea to be gradient descent based for our discussion, so that there are many other choices for even within the gradient descent first order methods family. But if you're doing optimization course, then you can look at it. I think it's simultaneous to this course, so you may not be able to do it right now. But yeah, we'll basically be just looking at first order methods and gradient descent methods. Okay, so let's look at data. I think I'll skip over this slide, which is mostly just about data handling for deep learning. These are not going to be small tables. These are not data that you query from a database, right? This is slightly different data, like images. They have to live on disk or somewhere, and they are huge. 1 megapixel image is going to consume some amount of memory. So there are some considerations that you need to have. But let me directly talk about augmentation. So augmentation is just the idea that you can have an xi-yi pair, which is the original data point, and you can actually change the xi to some xi tilde. Okay, so xi to xi tilde and still retain the label. So it's like you're creating new data points out of thin air. Okay, these data points. So what are these data points, right? So we'll see an example in the next slide. So basically, you had the original data point. You would use that for, of course, computing the loss and doing backdrop and all that. Now you're using not just one, but it could be more. One more data point, which is xi tilde comma yi, where xi tilde is some transformation of the original x. Okay, this makes sense for images, as you see in this figure. So irrespective of whether the original image, let's say this logo, or whether slightly cropped, slightly flipped, or slightly scaled image, ideally you would also want to still get the same class, let's say logos versus something else. Okay, so basically what you've done is augmented from one data point related to this original image to maybe like six times more data points in your training data. Okay, and they're not exactly the same, right? They're slightly perturbed versions. Okay, and the perturbations are very make sense naturally for images. It's like adding noise or adding some variation, but the variation is like very systematic, and that helps in having more data than you're started with. Like, because having labels for data is generally somewhat tends to be pricey the moment you go beyond like hundreds of images, because you have somebody has to spend time on annotating them, and they need to have that skill to be able to say the right label and all that. So you can get away with this type of data augmentation idea, which can augment your data and increase your data set size. So in ResNet, so at test time also you can do that same thing. At test time, like let's say you have been given a pre-trained model, you've been given a test image and you ask like, hey, tell me the class, you can just pass that image through the model, like do a forward pass, and you can get the class. But instead of just doing that, you can at test time also you can break up that input image and make these augmentations and pass all of them one after the other or together, whatever works, and then get all the labels and take the majority vote, for example. So it just robustifies your prediction. Okay, so in particular, the 2015 winner ResNet, it does a kind of specific scaling, specific operations, and cropping, and then does it both for training as well as while making prediction. This is, I guess, the idea, and other ways to augment include changing contrast, color, which you did not see, but translations, rotation, stretching, and you'll see that this is something that you can define. So these are done on the fly, by the way. These are not done. It's not like you have a data set of 1,000 images, then you augment it and create a data set of 6,000 images on disk, and then read it into your training loop. So while reading data into your training loop, you can do these transformations on the fly, so that you don't have to remember, because there's no value to remember these transformations and consume space. They're done on the fly. Okay, and you'll see in our code, in the example code, as well as in your assignment, you will kind of play with it. Yeah. So okay, now we're going to switch gears and talk about enhancements to the model, okay? Or enhancements to the modeling process. So there are several choices we have already seen, and we have to make sometimes. And as I said, the community has converged to some choices like, hey, 3x3 filters make sense now, whereas in 2012, when the first AlexNet made a big splash, they use a 7x7 filter. So later on, research, people found that bigger filters are not that effective. Maybe small filters are good enough. So that's how we came to a 3x3 filter, which is kind of the consensus today. It doesn't have to be that you have to stick with 3x3. You can change it, but seems to be the popular choice. Okay. Similarly, activation function, we kind of are talking about ReLU quite a bit. Previously it used to be sigmoid, and so there are some computational advantages. People have figured out that maybe ReLU, tweaking with ReLU, debugging with ReLUs are easier. So they tend to be the first choice generally for when defining a network. Okay. A number of layers, number of neurons. I mean, for at least the pre-trained networks, they have figured out by trial and error what's the right choices. When you make for your own approach, you kind of can reflect on a similar architecture. I mean, depending on your application, you kind of stick with what the consensus is. Okay, then this is all empirical, right? And similarly, there are a few more choices that you can make that do make a difference in terms of training, actually, especially for deep networks beyond, let's say, 10 layers or beyond 5 layers. It's very hard to train, which is something that is still a bottleneck. And that's why pre-training or transfer learning is very useful, because if you want to do that VGG 19 or whatever that 2014 version of a CNN, if you want to do it from scratch, it's very hard to train that. Okay. So the ideas are 3, and there are many ideas, but we'll look at 3. One is weight initialization, which is it's not really an idea, but choice that you want to think about, and also batch normalization and dropout. Okay. So weight initialization is just exactly, I'm putting the same picture that we saw in lecture 1, which is that it does play a role in where you get to, because that's precisely because the optimization surface or the loss function is all over the place. For some weight values of your network, it will be low, and for slightly, in the neighborhood of those weight values, like slightly perturbations, or the loss function may go up, and then for some, high amount of perturbation, it may again go down. So it's all, it's not going to be. So this picture is, by the way, just 1 dimension, but you can imagine like a hills and valleys type of a surface. Okay, if you want to imagine 3 dimensions. Okay, the loss surface. What you want to be is at the bottom of the valley, of the deepest valley. But how do you get to the deepest valley? You have to start from somewhere, because we're doing gradient descent. We're doing stepwise, starting from somewhere and then slowly changing, right? That's what we're doing, gradient descent. So we may not get to the, first of all, deepest valley. Okay, and we may actually get stuck in, we most likely will get stuck in local optima. The question is, can we avoid adverse consequences of not thinking about weight initialization? So there are so people try to kind of see if there are some rules of thumb that they can come up with, empirical choices that will help. Like instead of, like, for example, one way to initialize weights is just call numpy.random.random or something, right? It'll just randomly initialize uniformly between 0, 1, for example. But people have figured out some heuristics. I don't think I even mentioned the names here, but those heuristics, sampling from normal distributions and so on, of specific standard deviation, which depends on the how many hidden neurons you have and all that. So there are some rules of thumb that people have figured out, which are good choices. Okay? Again, as I said, this is a non-convex optimization problem for those who are interested in that type of field. So it's all the bets are off. Okay, this is an NP hard problem. Okay, if you want to use complexity theory words, so it's NP hard to solve this to optimality. So these are this is a trick. It's not a trick, but this is a concern that you need to be cognizant of and make use of it, especially if you're getting stuck somewhere. Try to change the initialization. Try to move away and explicitly say add an offset of +5 to all your weights or something. Okay, so that's the idea here. Yeah, and weights, of course, the weights, initialized weights also influence all the succeeding statistics, like activation statistics. Like, think of all the weights being super negative. That means all values are off, right? Irrespective of what x's are, you're going to be on the max of 0, x is going to be negative, so all your values are off. So you can imagine you're never learning if your weights are completely off. That's an extreme case, but yeah. Next is batch normalization, which is again trying to deal with this idea that, okay, once I define a network, I don't have a control on, if you think of any layer, let's say the fully connected layer here, like if you want to have a control on the magnitudes of these values, okay, so these values, for example, this vector here, which has a lot of, this vector here, those numbers, right? Those are numbers. If you just draw a histogram of those numbers, okay, if you like, you can compress, let's say, although there are a lot of coordinates here, just think of focusing on one coordinate, let's say. Okay, focusing on one coordinate. If I pass, let's say, 1,000 images, I'll have 1,000 numbers at that location, right? That neuron's output. If we just draw a histogram, does the histogram is it like all the numbers are like 100 and 100 and above, or are the numbers centered between 0 and plus or minus x, or like what is the statistics of that activation? Okay, that's what I mean by activation statistics. Batch normalization is an idea that, okay, irrespective of how many layers you have, let's add some extra post-processing after each layer, let's say con layer or a fully connected layer, extra post-processing, such that the activation vector, okay, is slightly transformed because of this post-processing, such that its statistics look like a normally distributed statistic, okay, which means that it looks like a Gaussian curve, okay, at each coordinate. Okay, so we want to kind of Gaussianize, and in fact, we want to make it standard normal. So it's as if the activations magnitudes are between exactly like -1 to 1 or whatever, -3 to +3, and like look like a bell curve. So that's what we're going to do, and that's called batch normalization. And this extra pre-processing influences everything else, because if the numbers are are recentered to between 0 to -1 to whatever, -5 to -3 to +3, and look like a bell curve, then the subsequent ReLUs will be active, right? So remember, if these activations are shifted to between -100 to -50, then the next subsequent ReLUs will be off, right? So if the inputs are completely negative, so this basically influence the activation statistics, and people have found out that adding this batch normalization layer basically influences the gradient flow, because if the nonlinearity doesn't kill off the gradient, then gradients can go all the way back, because the numbers are not too large or not too small. They're exactly, they're standard normalized, unit normalized, whatever, z-score, something like that. And so they're not, blowing up the gradients all over like huge numbers or making them 0. So that's the kind of idea here. So what is batch normalization, right? So let's, so there's two words there, batch and normalization. And so this is an idea which really uses the idea of a batch, okay, which is a batch of training examples. Remember, there was we used the batch word in batch gradient descent, where we were saying, hey, you don't have to look at all the examples. You can just look at a batch of 10 or 20 at a time, because if you look at all the examples and try to compute the loss, and then try to backprop through each of these examples, try to backprop, you'll have too many summation terms. Okay, so that's kind of computationally hard. So not computationally hard as in like complexity theory, but computationally hard is like it increases computation. Okay, so So what is batch, right? So let's focus on D neurons. Okay, so let's focus on, let's say we have fully connected layer. Okay, we have D neurons. D is like, let's say 10 neurons. Okay, so some hidden layer has 10 neurons. Now what you're going to do is have a batch size, which is so generally, by the way, batch size is something important parameter that you will kind of keep seeing in every assignment as well. It's you know, many of the PyTorch and TensorFlow, they by default kind of help you pass a batch, do a batch forward pass, and also compute the grains with respect to that batch. Okay, together. So instead of passing a single example and finding the grain with respect to a single example, or with respect to all of them, there's a batch parameter that you can use. Okay, so let's say there are n examples. Okay, let's say there are 50 examples and 10 neurons. Okay, capital N is 50 and capital D is 10. Okay, so what do? You focus on one neuron. Okay, so one neuron, let's say, corresponds to one column here. So for each of the 50 examples, so think of each example as one row here. For each of the 50 examples, that neuron must have produced some output. Right? So let's say 1, 2, -5, whatever. There's some 50 numbers that it produces. Okay. So what do? You kind of focus on that neuron and say, hey, these numbers are in some range. I want to standardize it. Okay, I just mentioned that. So how do you standardize it? You take that vector and subtract from each element, each coordinate of that vector, a common entry, which is the mean of that vector. Okay, expectation of that vector. So just the average of these numbers, just subtract it from each number. And then what is the variance of these numbers? That take the square root of it, which is a standard, kind of a proxy for the standard deviation. You divide by that. Divide each number by that. Okay, it's exactly the z-score computation from a regular bunch of numbers. Right? You do that. I added a gamma and a beta here just to show that this batch normalization procedure can also have its own parameters. Okay, which again you can fine tune. So which again you can learn using grain descent. But let's not worry about gamma and beta, or this Greek symbols here. They're just some constants for simplicity. And so what do you get after batch normalization? You had this original blue matrix of, let's say, or let's focus on only this column. You had the original neurons outputs. Now you have a modified bunch of neurons outputs whose modifications such that these numbers are kind of between -3 to 3, and they kind of look like Gaussian. Okay, so that's it. And once you do this normalization, you kind of do the exact same thing whatever doing in the next layer. So where all those batch normalization come? Typically, right, after a con layer, or after a fully connected layer. So there is some complication because at test time there's no batch. Let's say if there's only single image that's being input, then what these models, or for example in PyTorch, what they do is they do remember behind the scenes what the empirical stats, what these expectation variance was, so that they can plug in those numbers instead of not missing those numbers. Okay, so it's a computational trick, but it works pretty well. Okay, to train deep networks. So this is how it will look like. So previously, if there was some architecture, con pool, that, for example, this something like this. Instead of that, now you would add like an extra batch norm computation, and then let's say ReLU, or do ReLU first and then do batch norm. So there is no accepted consensus. So you can just you just need to add batch norm somewhere so that activations are in the right range. Okay. So basically, what empirically people have found out is that it improves grain flows, and is kind of makes you less sensitive to initialization and grain related issues, training related issues. Okay, so we will not talk about dropout today because we are kind of out of time. We'll discuss it towards the beginning of next lecture. Is that when we discuss? But again, another idea in a regular network to kind of add resiliency, to make it much it's kind of regularization. The same idea of regularization. Regularization helps not overfit and strengthens the model in some sense. Similarly, dropout also strengthens the model, for any deep network. So we'll look at that beginning of next class. So to summarize CNNs, because we're not going to revisit CNNs, we'll look at images in some other lecture, which is called GANs, or variational autoencoders, which are trying to generate new images from scratch. Like so that's we'll touch about images again, but CNNs in general will kind of pause here And next lecture onwards is going to be text for a couple of 2 to 3 lectures. Okay. So to summarize, exploring specific properties, hierarchy, locality, and locality of features at the lower layers, and spatial invariance. There are lots of design choices that still, there are a lot of choices that are exploding. As many of you have pointed out, how do we choose stride? How do we choose layers? How do we choose tensor sizes? So what we saw in the second part is some tricks, some ideas to kind of debug basically, or visualize, or how understand a little bit more about how your trained CNN is working. And then transfer learning is the tool of choice, especially if you have small data. It's an excellent starting point. And once you kind of explore that explore that transfer learning to its fullest, then you can think about actually doing from scratch, or doing what are later design decisions. And training tricks, we saw a data augmentation and initialization VASH-norm as some considerations. VASH-norm, by the way, is just available as a layer, so you can always add it to a neural network. Even Keras may be having it. We haven't seen dropout. We'll see that next time. Basically, what we've seen today, neural network training tricks is mostly focused on data and some modeling related choices, like adding a layer, adding some model related specific detail. On the optimization side also, which in addition to initialization, there are several approaches. Okay, ADAM optimizer versus SGD versus RMS crop versus there are like hundreds of methods that people have figured out. Some work well in some data sets, some work well in certain architectures. There is, of course, some popular, overall popular ones. You may have to try it in the assignment probably. Yeah, I think so. So there's a lot that goes on beyond the architecture definition. So much of this course is more about defining the architecture and talking about the forward pass. So how does input get transformed to get to scores? But then there's all this additional work of actually doing backprop, which hopefully the software does for you beyond assignment 1, and all these other considerations that actually lead to the success of the approach, right, over conventional approaches, or even make some applications possible which are not possible before. And we'll see several such applications, in subsequent lectures, like chatbots versus image captioning versus image generation, of realistic images and so on. So there are many different such applications. Okay, that's it for today.